And hello, students. This is going to be a quick overview of the normal distribution with a different problem. The final exam part B, I had some questions about. I just sent out a note, hopefully catching everybody before they turn this in, that I'm going to offer you some help that I had given the other student. So I'm going to base this on some of the questions. All right. So the basic type of information that we need to answer these normally distributed problems, okay, is we're going to need to know the mean of the data, and we're going to need to calculate or be given the standard deviation of the data. Okay. And the first thing to do is always draw, get yourself a normal distribution pictorial going here, as well as I can draw here. I'm trying to draw it as symmetric as possible. It takes a little trick to do that. Okay. All right. And when we look at the curve of this data, remember that the height of the curve is how frequently this particular value, whatever that value might be on the x curve, what's the frequency, what's the proportion of outcomes that this particular point represents. How many times did this happen when we took the readings? Okay, so you want to remember what this is all about. So the axis, the x-axis here, I'll draw that as straight as possible here, is going to be in your native units, okay? And I mentioned that, so let's contrast it to what else it could be. The other thing is that it could be in terms of z, or if you want to think about it, I'll make it square brackets, okay? Standard deviation, numbers of standard deviations. Okay, so our first scale in native units, what we'll do is we'll draw on our curve, we're just going to mark on the curve that here is our mean. Okay, so the mean is central to ideal data when you're talking about ideal data in a normally distributed world. Okay, and what's the standard deviation? It's like the average distance to the mean of all the points. Okay, so most of the outcomes occur around the mean. See this? This is our mean, and the height of the curve says things around the mean happen quite often. Okay. Then there's a group maybe in the midpoint where we have this descending part, quickly descending part of the curve, and then we have a flatter part that goes out possibly to negative infinity, depending on what we're looking at. Okay, so when we calculate the standard deviation, we do this calculation. We can come up with some kind of process. We have this equation. We come up with a process, and we come up with a standard deviation, and we say, okay, that's like a ruler. Okay, and it is going to be, let's say, we're doing the time it takes to get a bank report finished. I want to take it out of a tangible product world into something else. So we're going to say the mean is 16 minutes. Okay, and we're just going to say that the standard deviation on getting this bank report done is the standard deviation. So we're going to put that in minutes. Okay, and the average distance to how far away, the average distance to the mean, how far on average the outcomes are, is 2 minutes. I'm going to keep these numbers round. Totally making it up. I haven't run through this yet or not, but if I pick them round enough, that should all work out. Okay, so I'm going to move this down. I'm going to move this down a little bit. Okay, just remember that the native units we're going to mark on here. Okay, so what's our, when you start drawing these things, you'd say, okay, well, that's a number, whoops, come back here. That's a number 16. We put that marks our x-axis, okay? So if you remember that we have low values of whatever we're measuring here and high values over here, okay? So it increases as you go up here. We're representing the low numbers first to the high. We went through and we did a histogram. We did a histogram, and when we kind of saw how we took the random data and we organized it into little bins here, the lowest numbers first, then we put them in bins, and we came up with what Excel calls a column graph or chart, column chart. Let's take those off there. Okay, so that, remember, our data is now reorganized from a low value of in minutes. Well, I'm just going to totally make this up. Maybe we have some point out here where it only takes 2 minutes to do a report, and over here we might have 38 minutes to do a report. Okay, now I wasn't even careful to try to make this symmetric anymore, the real data here. Okay, so we're trying to get a feel for we're drawing this and getting a feel for what the native units, where they end up here. But we were given that 2 minutes is the standard deviation. Think about that as like a little wooden ruler that's too long, Okay? And so the standard deviation, if you know it's 2, we know that if we're going to just rough draw this out, that the first standard deviation is on the shoulder, the second is on the steep part of the curve, and the third part is further out. Now, so remember that this distance, this is your standard deviation. We go out another standard deviation. We're just marking off on the x-axis. 1 standard deviation, 2, 3. So I'll mark that as 2, and that is 3. We've gone out 3 standard deviations that way. And we go here, here, and here. As I said, we do know a property of the normal distribution is that the standard deviation is something on the shoulder here, and the second one out is on the steep part of the curve, and the third one is down where the tail gets thin. That's about as far as you can really take it, but you should know that. You should understand that normally distributed data, that's the way it's a property. It's built into the curve because the standard deviation describes how much variability there is in a curve. Okay, so 16 minutes. If we come down 2, okay, we're just going to mark down 2 minutes. That would be 14 minutes, 12 minutes, and 10 minutes. Now we just use those numbers to mark them here. 16 plus 2, because we took our ruler, we measured out 2. It's going to be 18, 20, 22. Okay, so when I said draw the properties of the problem, or draw this, that's what I'm saying. Get a feel for where all this goes. Okay. All right. So the first part was drawing it. Now, we said that we could also think about this in Z's. Z is how many standard deviations we are from the center. So right at the center, we're going to be 0 from the center. Okay. If we go down 1 standard deviation, that means we're down 1 standard deviation minus 2 standard minus 3. So this is the other scale that we can use. We can turn our native units into 1, 2, 3. And this depicts what we call, it's plus and minus 3 sigma. When we have that kind of system, we call that a 3 sig system, a shorthand talk or shortcut talk for what plus and minus 3 means. That means we're dealing with a 3 sig system. That means plus and minus 3. Okay? All right. So that's how you first draw it. And then if a manager comes in and says, well, listen, I know that unless the time that it takes to get one of these reports done, if it's between 15 and 17 minutes, I will accept it. Okay. If it takes less than 15 minutes, that means somebody doesn't know how to do it. I'm just interpreting that right here on the fly. I'm saying, why would someone reject it if it took less time? Well, it might need to be reviewed. Okay. So it's too fast here, okay? Because our time is low, it means the rate is fast, okay? So these are faster. By some kind of study, the manager knows that when they're done too fast, then there's something wrong. Someone didn't do all the computations on them. And if it goes greater than 17, that's too long. I'm not going to accept it. We're going to have to go into review. So that's your rejects are anything less than the lower limit, okay? Or we often call this the lower specification limit. The customer is telling us, here the manager is our customer. The customer is telling us, my spec says 15 minutes and 17 minutes. I won't take anything between those, but I am sure there's something wrong if it goes outside that. Okay. So let's draw that on the curve. Now, these are the ones that are like carved into stone. Okay. Our process is what we show right here. Okay. I would probably say also before I leave this point is that yes, the manager is saying that 16 would be a good average for this, but I'll accept anything down to 15 minutes and anything up to 17 minutes. And I gave the reasons, the rationale why that manager, she would reject those. Okay, so they're going to reject something out of here. Let's put that on the curve. So we'll use a little bit of different color here. We'll say, where does 15? Oh, 15 ends up right here, and 17 ends up right here. Now, I've really kept these all symmetric. You can't depend that in real life that all of these specs and your numbers and data are all perfectly symmetric. Okay, but here we're saying that you're going down by 1 minute and up by 1 minute. Okay, so that what we did is we just plotted on our curve. Whoops, that's 17. Oop, get rid of those. Okay, that's 17. All right, so we're going to accept everything between here, and we're going to reject, what could I use? Orange? Yeah, orange. We're going to reject anything, that doesn't really show up very well, anything under our curve there, and anything under our curve here. These are proportions, areas under these curves, right? Okay, so the orange, which isn't showing up too well here, I'm sorry. Maybe what I can do is make it fat. Okay, so orange, that's way too fat. Hold on. I never go with that chubby. Let me go back over here. So orange equals what? Scrap or reject. Whoops. Reject. Okay, so we're rejecting everything in the orange, and we're keeping what's our proportion of things that we're going to keep? Okay, so the proportion of what we're going to keep is in here between 15 and 17 minutes. Okay, so what are we going to do? I'll make it a little bit smaller so I can write a little bit better. But purple works pretty well. Well, our special formula for just this kind of thing that we use over and over again is what? Norm.s.dist. Okay, and what does it take? It takes a z, is a number of, is a unitless, dimensionless ratio of standard deviations. Okay, so it comes in terms of like a standard deviation and not minutes. Okay, so we're now not in the native units. Now we're using these numbers, which are dimensionless. Okay, so we're going to put in a number that represents where on this curve we are, and the word true, and that makes the formula run correctly. Okay, so what is a z? Z is how many standard deviations are we down when we're at 15? Okay, our norm.s.dist gives us the area under the curve, the proportion compared to the whole curve, like a probability or a proportion rather. Yeah, probability or proportion of the curve up to the point that we put in here, and we have to put it in as a form of a z. Z is just how many standard deviations are we down at 15, okay? So to get that, if you look at it, there's minus 1 standard deviation, and here's 0 standard deviations, and by golly, 15 is right between 16 and 14, okay? It's right between there, so it's half that distance, so it's half a standard deviation. Z is equal to 1/2, okay? But now I'll show you the formula. I want to show you the logic behind it. We're only a half of a standard deviation down there. How do we really get Z? We're going to get the same answer, but if you depend on the formula, is you're going to take your point of interest, how far is it away from the mean, and you're going to divide by your standard deviation. So the point of interest is 15 minus 16 over 2. 15 minus 16 is minus 1 over 2. And we can add that now because now it makes sense because the direction matters here. We are down at 15, we are down a half a standard deviation. Okay, so let's calculate that. Let's calculate this area to the left. Okay, so that's going to be equal to norm.s.dist of what's our z? Minus 0.5. True. You can either put this in uppercase or lowercase. It doesn't matter. True. Okay. Right. So the z, it just shows that our point of 15 minutes is it's just a half of a standard deviation down. I'm trying to give you the rationale logic connected to the real world kind of thing here. So we have minus 5 in there, and that's going to give us all of the area, the proportion of the area to the left of that line under the curve. Okay, hit that, go in there. Okay, so at a z of minus 0.5, 30 point, I'll turn it into percentage. All right, so we can either say the probability is 0.3, or the percentage is this, and usually I like to add at least one. Try that again. I want to oh, I know what was yelling at me for. I want to add at least one decimal place to give, it's rounding it. It's a little bit not precise enough. Okay, so I just increase the precision here to one decimal place. All right, so it's 30.9. It's rounded to 30.9% of the reports are too fast. I can tell there's something wrong. No, that came back too fast, right? And then we need to look at the area to the right here, okay? Because we're going to reject everything greater than 17, okay? There's two different ways to look at this, okay? I've said that we were using a very symmetric curve here. I mean, it's ideal data, right? Okay, so there's two ways you can look at this. One of them is, so we have A here, and we have A prime. They're going to be equal to each other. Those areas are equal to each other because we stayed symmetric. Okay, we went down by 1, we went up by 1. Okay, offhand, we should be able to say, well, the upper limit that our customer or manager gave us is what? It's 1 over 2. It also is an honest 1 over 2. It's not minus 1 over 2. It's an honestly 1/2 of a standard deviation above the mean. Okay? Now, if we use the norm.s.dist formula, okay, if we just go ahead and put 1/2 in here, if we put half in there, we are going to get the area up to 17 degrees. We're going to get all this area down here. Okay, so this shows us two different ways that we can speedily calculate the reject rate of our bank forms. Change it to green. I think that shows up all right. Okay, so the first way is by symmetry. We know if we're down by -1, if we go up 1 to 17, A prime is the same as A. So just take 2 times that number and you're done, right? You have the area of A we figured out. Well, we know A prime is also the same equal area. So our reject rate is 2 times that, or whatever that comes out to be, to 61.8%. Excuse me. All right. The other way to do it is go ahead and punch in the formula with a half in there. Okay. This is the longer way, but you're going to come around to this pretty quick. So norm, there's no real need to use this when you have symmetric. Norm.s.dist of what? 0.5, comma, true, so you don't really need to put that in uppercase, but you have to spell it right. Okay, so what's going on with that? That number there is everything to the left. Okay, that's what our formula gives us, everything to the left of that number. Okay, so we want everything to the right of the number. So we're just going to go 1 minus that, the complement of it. Hey, that looks like the same number we got before. Okay, so then your area would just be equal to, this is as if that's area A, and this is area A prime. All right, so we could add them together is equal to that plus that. Okay, so that's our reject rate, everything outside the 2 goalposts that the customer or our manager gave us. Okay, so that would be your reject or fail rate, and your yield or acceptance rate. What is that? That's just equal to it's the not the opposite, but the complement to that. It's everything other than things that are on the wings. So it's going to be equal to 1 minus that number, or 38.295. Okay, so the reject rate is 61%, and our yield is 38%. In our business problem, we have to decide whether that's good or not. I haven't put any other kind of normative statements on this as to what it should look like, okay? But that's the numbers. It's going to fail about 61%, or almost 2/3 of the time. We're going to not make our manager happy, and we're only going to make them happy 38% of the time. But as I said, I'm not going to go any further with the description of the problem. You would look at it. Maybe that's really good. Maybe that's very much improved from last year, where 92% of things were getting rejected. Okay. And this is a very good example in service industry of what you're looking at. You're trying to reduce human error, getting these things sent back. Like this is where AI, you hear all about AI. This is where AI would scan these and start taking the data in and digitizing it and doing it a better job. That's an example of something where artificial intelligence would work. I'm not going to put anything else to here, but you should be able to take what I gave you here and get back to running the description of this other problem that I gave you, a kibbe strand problem. Hopefully that helps. And I will be near my email here for the next 48 hours or 36 hours or whatever number that it is until midnight Sunday. So you can email me. I'll keep taking a look to see if anybody's emailing me, but hopefully this should help out.